Okay, my name is Sidney. I'm going to present the paper EvoDynamic, a framework for evolution of generally represented dynamical systems and its application to criticality. Okay, yes. Here's the overview of the entire project for the EvoDynamic framework. This framework will be based on dynamical systems, such as sparsely connected networks. Such networks are used in reservoir computing paradigm. This paradigm exploits the dynamics of the reservoir or dynamical system to linearize nonlinear separate input data that comes here from the input to the reservoir. And this allows linear machine learning systems or just one single neural network, one single layer of neurons, artificial neurons, to be trained in this pre-processed data that comes from the reservoir. EvoDynamic is going to evolve as well the topology of the network, the communication rules that change the states of the connected nodes, in the learning rules as well, that modify the communication rules depending on the states of the nodes, a history of states of the nodes. These evolution are going to have some goals. One of the goals is to improve the quality of the dynamical systems to be used as reservoirs, to model the behavior and dynamics of physical reservoirs, and to produce an agent that can learn interacting with the environment. The physical reservoirs that I mentioned is the focus of the Socrates project, and they are the biological neurons over microelectrode arrays and nanomagnetic ensembles. Okay. The EvoDynamic framework is implemented in Python, and it's based on TensorFlow version 1. Here is the link for our open source repository. Dynamical systems, this framework will simulate dynamical systems that can give rise to the emergence of complex dynamics. They are the cellular automata, coupled mat lattice, random Boolean network, equistate network, and liquid state machine. They all have different characteristics, as we can see here. But with our framework, they are going to be generally represented. Here is the simplest dynamical systems that we mentioned, the cellular automata. This is going to be our focus in this paper. Here is an example of one-dimensional cellular automaton shown in the animation. And it changes this string of binary values, change its states according to a rule that is that verifies the three neighbors, and then it changes the center cell. So one string is replaced to another string according to this rule. That is rule 110. Here is the representation, the alternative method to compute the next state of a CA. We not need to care to go into a slidey window verifying the neighborhood of each cell to change the center cell, for example. We use dot matrix, adjacency matrix, and dot product. Okay, here in A, the figure A, we see a 2D cell automaton, and its binary states 1 and 0. Here is the neighborhood. We have 4 neighbors for the center cell. And here is the generated adjacency matrix. If you follow here the row 5, it's connected to, has neighbors 1, 4, 6, and 10, and 9, as expressed here. Here's our adjacency matrix. We just converted the neighborhood to a adjacency matrix. And doing a dot product with the states of the cells, you can see that only the cell with index 5 is the one that has state 1. It's here. And when we do the dot product, the result is the number of neighbors that are active. Here is for 1D cell automaton. For 1D cell automaton, it cares about the pattern of the neighborhood instead of just counting the neighbors to generate the next state. This is what the animation shows. This is the elementary cell automaton. So here we have our GNC matrix, all the three neighbors, but we have a different approach. Instead of adjacency matrix with just 0 and 1, we assign weights for that can represent, in the end of the dot product, a pattern code. And we can see that now the right cell, the center cell, and the left cell are represented with number 4, 2, and 1. So with this CA with just two binary two states, we can create kind of pattern that it comes from a binary string to an integer. And here we express here in this pattern code is basically a binary string to it represent its integer. And after the dot product, this is what it does. It just converts to the integers, the binary codes. And then we can have a function that converts this pattern code to the next state of the cell automata. Okay, and here is an example of application of using the EvoDynamic framework. The stochastic CA is defined by this equation, where P is the probability of a cell to be equal to 1 when given a neighborhood pattern, and the states are just 0 and 1. Criticality is known to allow computability or useful computation in a complex dynamical system. The avalanche size distribution is calculated by the cluster size of a chosen state in the space dimension. The avalanche duration distribution is calculated using the cluster size of a state in the time dimension. For our CA with just 2 states, the number of avalanche distributions is equal to 4. They are the avalanche size for the states 0 and 1, and the avalanche duration for states 1 and 0. The evolution of stochastic CA towards criticality is performed by a genetic algorithm. The CA has 100 cells, or 1,000 cells, that evolves through 1,000 time steps. The population has 40 individuals, and we run it through 100 generations. After the simulation of the cell automaton, the following objective scores are calculated, and they are the normalized number of histogram bins. Here is the equation for it. The coefficient of determination of complete linear fitting, Kolmogorov mean of statistic, the estimated power law exponent, and the unique states. This is all to try to fit the avalanche distributions to a power law, and closer to it, greater is the fitness score. And here is the end of the fitness score. Okay, and here is after 5 runs of the genetic algorithm, we obtain the following results for the 8 neighborhood pattern for our CA. Here is the neighborhood with 3 neighbors, all the patterns, and the probability P of the next state producing a state 1 for the center cell. And here are the fitness scores for every objective and the total one that is our fitness score. And here at the right side, we can see the generated cell automaton, and this produces, it looks like avalanches, and these produces also complex structures that can be used for computation in reservoir computing, for example. And here is the resulting avalanche distributions for size and duration of state 1. The state 1 is the color white. And that reached criticality since the avalanche distribution follow the power law that is estimated here in this dashed line. And here, the x-axis is the size of the avalanche, and here is the probability. How many, basically, is the normalization of how many of the avalanches occur. And we have a power law here, and also a power law here in the duration. Okay, and to conclude, we introduce alternative method that implements a cell automaton using TensorFlow, its application of evolving CA towards criticality was successful. For future work, we plan to add other CA dimensions like 3D and other dynamical systems in the framework. We also plan to evolve towards self-organized criticality. So this is our work. I would like to thank my colleagues and institutions involved in our work, and I would like to thank you for your attention.